So in our previous videos, we showed optimizing the geometry on the right side of the page in Ansys Discovery and meshing this geometry in Ansys Mechanical. In this video, we're going to show how to apply loads and boundary conditions to this geometry, as well as the baseline geometry for the quadcopter legs that we started with, in order to get a one-to-one comparison of the uh, reduction in stress and mass. So we're just using very simplified load conditions. So of course the stress results are quite low, but we can compare them in a one-to-one manner. So we can see ultimately that this optimized geometry has a 33% reduction in mass, nearly a 50% reduction in the peak von Mises stress, and almost an 80% reduction in the total deformation of the legs. So let's have a look at how we set these up in Ansys Mechanical. So first here we have our baseline quadcopter leg geometry loaded into Ansys Mechanical, and we can see how we've set up, so we have just applied a simple mesh and we're able to get a nice tetrahedral sweep on these leg bodies, or sweepable bodies. And we've applied the same load conditions that we applied in Ansys Discovery. So again, just simplified loads in both X, Y, and Z directions to these 4 locations on the base of the legs. And we have 8 load cases, so we're varying the directions of the X and Y forces. We've also applied a fixed support to the top of the legs where they would meet the rest of the quadcopter body, as well as moments that are varying positive and negative across the 8 load steps on the base of the legs as well. So next we've initiated a solve of this, so we could just quickly, once we have these forces and moments and fixed supports, we can just quickly right click and solve. But I've already done that here, and we can see that we have a peak equivalent stress of around 3.1 MPa and a maximum total deformation, which is at the bottom here, of uh, around 0.01 millimeters. Now for this equivalent stress, I reported a slightly lower quantity because this edge here is at a bit of a stress singularity. So in this case, I may want to turn on the edges. So here under the result, I can turn on show elements. And instead of just reporting the maximum result, I'm gonna do a result probe 1 element away to get a reading of 2.77 MPa, 1 element away from the singularity. So now let's move to our optimized geometry, where I have set up similar load cases, force, moments, and fixed supports. And again, over 8 load steps. And I've solved the results. So on the right side of the result here for the equivalent stress, I can see the maximum from each of the load steps. So actually the maximum is occurring in this 3rd load step. So I've made this equivalent stress to be a display time of 3 seconds for this 3rd load step. And we can see here in this result that instead of having the peak stress right at the point where the legs meet the quadcopter body, we've moved that maximum stress location away from that location to just a location on the leg of the quadcopter landing gear. So we're quite happy. This is we've almost cut the maximum stress in half. Additionally, we can check the peak displacement, where previously maybe the peak displacement was just at the bottom. Now we're seeing we've changed the location of the peak displacement as well. That's all for this video series. I hope you learned a few things and wish you the best of luck in your quadcopter design. Thank you.